Today, we're going to be talking about sums sigma notation. That sigma, the Greek letter sigma, is the symbol for a sum. In fact, if I'm not mistaken, there's one on my back at this moment. Sigma notation consists of that sum notation, an index. Now the index could be I or J or K. For our purposes, in order that we'll all be on the same page, we'll agree to use K as our index. The lower limit of summation is right here. It could be any integer, but we'll agree to use 1. Right? You could start at 0, you could start at 2, you could start at a negative number, but we'll agree to use 1. Up here generally will be another number, but I'll just write n for now. That's the upper limit of summation. So, and over here would be some explicit rule for finding the kth term. Okay? The first term, the second term, the third term, all the way up to the nth term. All right, so we have the sigma, the sum symbol, the index, the lower limit of summation, the upper limit of summation, and a rule for finding the kth term. That is sigma notation. Well, let's take a couple of examples, just so we see. Suppose we give a very specific upper limit. K equals 1 to 4 of the simplest. Say K. All right? The first term is 1. The second term is 2. Third term is 3. Fourth term is 4. If we evaluated that sum, we simply add those up, and we get 10. How about if we have something like this? K over K plus 1. Right? The first term, since our lower limit is 1, is 1 over 1 plus 1. The second term is 2 over 2 plus 1. And so on through the fourth term. That's sigma notation. In addition to that, we could even have a situation where we have negatives. For example, and let's see, well, let's go the other way here. Let's do something like this. I'm going to take a sum and then analyze the terms to see how to write the sigma notation. So, let's do something like this. Okay. Now remember what we have here. We have the first term, the second term, the third term, and the fourth term. So 1 tracks to 3, etc. Now notice what these numbers do. The 3 is 2 times that plus 1. The 5 is 2 times that plus 1. 2 times plus 1. 2 times plus 1. So part of our sigma notation here now we have 4 terms. I don't have to use 4, but there's no point in writing more than I need. Okay, so we know that part of our sigma notation is 2k plus 1. These are our k's. But how do we account for the alternating negatives? Well, we can do that by multiplying by -1, but not every term. The odd number terms are positive. Right? Now, if I put k here, the odd number terms would be negative. The first term would be -1 to the 1, the third term would be -1. So I can do something like this. So what I have here, and let's make sure that it works, -1 to the k plus 1 times 2k plus 1. Well, the first term would be -1 squared, which is 1, times 2 times 1 plus 1 is 3. The second term would be -1 cubed, which would be negative, and then you'd have 2 squared, 2 times 2 plus 1 is 5. So we can write the sum in sigma notation. Let's try some others. Well, actually, let's take a look at algebra rules now, because there are specific algebra rules regarding sums. First one is quite simple. That is, if you have two different sums that you are summing, what we have is exactly what you would expect. First algebra rule. Second, constant multiple rule. A constant multiple can be taken out outside the sum. And in fact, we actually did this when we looked at those finite sums in a previous lesson for approximating the area under a curve. Because the width was a constant 1/4, we pulled it out and then added the heights together. That's essentially what we did at that point. Now, suppose we don't have a k. All right, this is the constant multiple rule. Okay? This is just a sum and difference rule. This is constant multiple. This is a constant value rule. Suppose we don't even have a k. We just have some constant here, any number. In that case, what are we doing? Think about this. We have a sum of n terms. But if all of the terms, if each of those n terms is just c, we have c plus c plus c plus c n times. So in essence, we have n times c. That's just constant value. Don't confuse that with constant multiple. So those are the algebra rules for finite sums. Now we're going to take a look at three special sums. Three sums that we are going to use. When we get to our lesson on the Riemann sums, you're going to want to have these available. Our three special sums. The first is the sum of the first n integers. That is one plus 2 plus 3 plus 4. All right? The sum of the first n integers. It turns out that that is this. Now, anybody who has studied this has heard the story of how this was arrived at. This was discovered by an elementary school student in the late 1700s in Germany named Carl Friedrich Gauss. And as the story goes, the teacher in his elementary school class wanted to give the class something to do to keep them busy for any length of time. If you've ever taught elementary school students, you will understand that teacher's dilemma. Sometimes you just need a break. Unfortunately, he had Gauss in his class. And while the rest of the students may have taken a lot longer, Gauss did this in seconds, a minute. The story is that the teacher said, add up the first 100 integers. 1 plus 2 plus 3, all the way to 100. Gauss saw a pattern. That is, he saw that these 100 integers could be written as pairs. The first and the last. 1 plus 100, 101. The second and the second last. 2 plus 99, 101. 3 plus 98, 101. 50 pairs, each adding up to 101. 50 times 101, 5,050, he was done. Another way to look at it is to say, well, suppose I had these and I decided, hey, let's write them backwards and see if that helps. In this case, you have 100 columns, each of them with a sum of 101. 100 times 101. But these represent those integers from 1 to 100 twice. So you take that 100 times 101 and divide by 2. And again, you have 50 times 101, 5,050. All right, sum of the first n integers. The sum of the first n squares. Okay, let's just use it. Sum of the first n squares. Suppose we wanted to add up 1 plus 4 plus 9 plus 16 plus 25 plus 36. All right, here we have 6. N equals 6. So the sum of those should be 6 times 7 times 13 over 6, boom, boom, 91. Let's take a look. 5, 14, 30, 55, 91. The sum of the first n cubes. Yeah, write that. By the way, if you get good at this, perhaps you can make a few dollars at your next party. Give someone else a calculator and ask them to add up the first 100 digits while you do it in your head. Or the first 20, or the first 50, or the first 50 squares, whatever it happens to be. All right, k cubed. Well, this is really neat. This will look familiar. The sum of the first n integers squared. So the sum of the first, well, let's just take the first 5 cubes. 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. All right? According to our rule, that's the first 5, that should be 5 times 6 divided by 2 all squared. Well, that's 30 divided by 2 is 15 squared is 225. Those should add up to 225. 9, 36, 100, 225. And that's the sum of the first 8 cubes. We'll be using them. So, know them. And that's all.